Okay, soft K means it's much softer than the hard K means, of course. Well, because we'll find out why. But as you saw in the previous episode, there is a problem with K-means that the points that closer to decision boundary are accounted for equally with the points that are lumping clustering together right in the heart of the cluster or particular cluster. And the point is that this borderline points are only assigned to one class and assigned hard, and then they shift the mean towards them, even though only there is one or 2 points. But still, I don't find it specifically helpful um, when this happens, and people were thinking about it for quite a while. So here's what was suggested, derived, and works quite well, and also has interesting parallels and consequences in the density estimation. So what we need to do is relax responsibilities. Let's try instead of hard responsibilities when each point had a binary vector with it of whether this particular point xn belongs to one of the classes. Let's make responsibilities continuous. So let's say it's kind of likely to belong to the first one, not so likely to the second, and then maybe a little denser to the third. So soft responsibilities are, it's possible to make them learnable. So it's relaxation. We took a binary vector and relaxed it into a continuous vector. Um, what does it think about it? Think about what it reminds you from the modern machine learning, deep learning, and such. But our goal is sum to one to make sure point is assigned to at least one cluster, right? Not only we want to have continuous assignment, well, instead of hard assignment, we also want to have this assignment to be convex. Again, that the sum of the coefficients is equals to 1. Additional thing in soft k-means, we will need yet another parameter that is there just to signify how much of data is needed or belongs to one point. And we need that stiffness parameter. So soft k means the algorithm stays, at least the skeleton stays exactly the same, and there is only one slight change now with the soft assignment because our responsibilities are now continuous. Here, how we define them. Each point, for each point, we compute a soft assignment to each cluster or compute responsibility for each data sample. Uh, this is our distance function, and this is the distance function for this point to every other mean or every mean, all of the means, all of the centroids. This is just the distance to the current centroid. What does it remind you of? Of course, softmax. So basically, what it says, blah, 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 is that in every column, all of the elements sum to 1. The int, that's it here. For any n softmax exhibits this property that everything maps to 1. But because these weights are continuous now, when we take this row in the next step in the update, they will be used and utilized to a greater good. Here's what happens. nothing happens. The update step is exactly the same as before, only this values here now is that, let's denote our x again. Each column here is our x, and it's d-dimensional. But if we take this binary vector or make it non-binarized by multiplying x times the indicator or scaffolding vector that we're discussing here today, and you get your mean. So that's slightly magical and quite interesting. Let's see something about the soft k-means. So in soft k-means, we define the stiffness parameter, but our linear scale or length scale can be defined as 1 over square root of beta. So let's see what happens from the large sigma to the small sigma. When the sigma is large, all of the means are the same. So when beta is small, all of the means are the same, and this is the four means example, and they're sort of like getting stuck at the coral reef. Um, yeah, so gradually we're increasing our uh, or decreasing, actually we're increasing our stiffness and decreasing our length scale, and the more we decrease our length scale, sort of the smaller, the tighter the clusters. Eventually we'll capture four clusters with soft K. How can we improve soft K means? That's the topic of our next lecture or one of the next lectures.